So today we're going to be solving systems of equations that have some unusual answers. And we are going to do it both algebraically and on a graph. Alright, so let's look at this first one. 6x plus 3y equals 12, 2x plus y equals 6. Let's do it algebraically first. Okay, so notice the x's and y's don't match up. But if I multiply this equation by 3, then the x's will match up. Alright, so 3 times 2x is 6x, 3 times y is 3y, and 3 times 6 is 18. And if you're not sure how to do this, I do have a video explaining how to solve equations like this. The link is down below. Now, I'm going to take the other equation, write it underneath, and notice when I do that, the x's match up. So now, if I subtract the equation, I can eliminate the x's. All right, so let's do that. 6x's minus 6x's leave me with no x's. But notice, 3y minus 3y eliminates all the y's also. There's nothing left on the left side, so I'm going to write a 0. On the right side, 18 minus 12 is 6. And look what happens. After I subtract the equations, I'm left with a math equation with no variables, but it's also an untrue statement. It says 0 equals 6. 0 doesn't equal 6, and 0 can never equal 6. This is not a true statement. So what this tells us, because there's no variables involved in here, this tells us that there is no solution. In other words, there is no possible xy combination that would work for both the top one and the bottom one. All right? So there is no possible combination that's going to work for both. All right? Now, let's see what that looks like on a graph. Okay? Remember, the solution to a system of equations is the point of intersection, meaning if I graph these two and find where they intersect, that's going to be the solution. So let's do that. I've got 6x plus 3y equals 12. I'm going to graph the intercepts. If x is 0, what does y have to be so that 3 times y equals 12? 3 times 4 equals 12. So the combination 0, 4 is one of my intercepts. And if y is 0, what does x have to be so that 6 times x equals 12? X has to be 2. So the combination 2, 0 is my other intercept. And if you're not sure how to do this, I do have a video explaining how to graph equations in standard form using the intercepts. All right, so there's the first equation graphed. Now let's do the second one. All right, if x is 0, what does y have to be so that y equals 6? Well, that tells me y is 6. So 0, 6 is an intercept. And if y is 0, what does x have to be so that 2 times x equals 6? Well, 2 times 3 equals 6, so 3, 0 is my other intercept. There it is. So if I graph this, there's my line. And again, remember, the solution to a system of equations is the point of intersection. And what do you notice about these two lines? They run parallel to each other. So they will never intersect. Since they will never intersect, there's no solution, which is exactly what we got algebraically. All right, so on a graph, no solution will look like two lines parallel that never intersect. In algebra, no solution will look like an equation with no variables, but a number equal to something that it's not. For example, 0 equals 6, an impossible situation. All right, let's look at our second equation now, or second system of equations. All right, 3x plus 5y equals 15, 6x plus 10y equals 30. All right, let's do it algebraically first. Notice the x's and y's don't match up, but if I multiply this first equation by 2, then the x's will match up. So let's do that. 2 times 3x is 6x, 2 times 5y is 10y, 2 times 15 is 30. All right? Now I'm going to take my second equation, write it underneath here, and notice if I subtract these, I'll be able to eliminate my x's. So I'm going to do that. All right, 6x's minus 6x's leave me with no x's. But look, 10y minus 10y leaves me with no y's also. So again, I end up with nothing on the left side. On the right side, 30 minus 30 equals nothing, 0. So notice, in this situation again, we are left with an equation with no variables, but this time the equation we have is actually a true statement. 0 equals 0. That's true. 0 does equal true, as opposed to up here, 0 equals 6. That's not true. 0 equals true. 0 equals 0 is a true statement. So we can say that this has infinitely many solutions. Infinitely many solutions. What that means is that any combination that'll work on that first equation will also work on the second equation. So there's a lot of different possible answers for this one. Okay? So any combination that works on the first one will also work on the second one. That's what that means. Okay? Now, let's see what this looks like on a graph. So, I'm going to plot the intercepts once again. For this first one, if x is 0, 5 times what equals 15? Oh, it has to be 3. So 0, 3 is one of my intercepts. And if y is 0, 3 times what equals 15? 3 times 5 is 15. So 5, 0 is my other intercept. So let's draw that in. All right. Now, let's do the second one now. If x is 0, 10 times what equals 30? 3. 10 times 3 equals 30. So 0, 3 is my intercept. So it's the same one here. And if y is 0, what does x have to be? So that 6 times x equals 30. X has to be 5. So 5, 0 is my other intercept. So that's going to go here. And notice what happens here. My intercepts on my second equation are the same as on my first one. In fact, when I draw my line in, the second equation makes a line right on top of the first line. Now remember, your solution to your system of equations is any point of intersection. And notice, the lines are on top of each other. So they intersect everywhere. Their point of intersection is everywhere on their lines because they're the same line. And that's what infinitely many solutions looks like on a graph. The lines are on top of each other. So everywhere the line is, it's an intersection point with the other line. All right? So that is what infinitely many solutions and no solutions look like algebraically and on a graph. If you found this video helpful, I hope you did. Please hit that like button, also subscribe. But with that being said, good luck on your math, and I will see you next time.